skip the lecture note. Of course, you can record. Okay, you can record during the lecture, so you can review after the class finish. Okay, Chami.
Yes.
Do you understand what I'm saying?
Yes, I got it.
Okay, so please note this. Okay, so I will in charge this class for first 6 weeks. Later, Dr. Hai will in charge. Uh, so the contents of this course or these objects will contain 3 parts. The first part will be his conduction in solids, and the second one will solid state diffusion, and the last part will fluid diffusion or momentum transport. So I will recap the first part is his transfer or his conduction. Okay, so this is the course contents. Okay, if I talk something you don't understand or you feel that it's too fast, so please, okay, remind me. Okay, this is main references I use in this course. So please take note or capture screen or you record for the reference. So the first one will be material science and engineering S edition um, by Willie in 2011. But the main book I use for this course is Chanport's Phenomena, okay? Second edition, Willie 2007, or you can use 7 or 8 edition. This is second edition is quite old, so the latest version is 8th edition. So you can download the latest version. Of course, you also can have some other book for heat and mass transfer. That is heat and mass transfer third edition, Springer, author Han Dieter Bar. Okay, and some other book for this course. So please remember that this course contains a lot of equation. Okay, and the exam is all about the solving the equation and calculation. Okay, please remember that. Okay, that is reference. Okay. Um, so for this project design, so you will learn all about the fundamental thing for which uh, for the designing process. So of course, the fundamental things you will study is transport phenomena and chemical reaction between different sizes of pressures. Why we have to study in this? Okay, so chemical and metal and other material produced or other equipment. Okay, equipment uh, are produced by means of series of units operation. which will involve to transport phenomena. It's involved to chemical reaction between different phases. So that's why you have to study all these things before you can design your equipment, or you can design your process. The process can be a production of steel. Okay, it can be a casting process. It can be rolling. Okay, the design process can be involved to design for heat exchange, also heat exchange. For example, heat exchange in the radiator in car, okay, to cooling the engine, or the heat exchange for air conditioning, okay, air conditioning in the room. So it's very important. Or for example, some bearing for a machine for car, okay, bearing. So you need you need the bearing. It have surface. We have hard surface, but the inside still have toughness. So you need to use carburization process. It means you use carbon to penetrate to the surface of the material uh, to make it become harder. So that is so to know how to design that process, you need to know what happened. Okay, uh, when the carbon penetrates to the surface of the material, how fast, how depth the carbon can penetrate to the surface of the material. Okay, what's the temperature you want to use? Okay, how long you need to use? So that's all the thing you need before you can design the process. This picture is one illustration for one process of casting some slab, okay, slab from molten steel. So you need to pour in a mold. So the liquid or molten steel will become harder, okay, and during harder, so it will this uh, subject will roll, okay, and the of course during this process you have exchange heat is uh, sorry, I have sorry, wait for a minute. Okay, sorry for interrupt. Okay. So we will continue the class. Okay. So in this course, we will study chatbots phenomena. The subject of chatbots phenomena includes closely related topics, which including fluid dynamic or chatbots momentum. Okay, so this involves to the chatbots of momentum. So Dr. Hai will in charge this topic. Okay. Following is heat transfer. Okay, this are dealing with transfers of energy. So I will in charge this part. Okay. The last one will mass transfer. Okay. This concern with the transfers of mass of various chemical pieces. Dr. Hai will check this part. Okay, so this is a topic of this class. Okay, so please take note this so you have overall picture about the class, so you know what we will study. Okay. Okay, so what we will study in Champort's phenomena. Okay, so Champort's phenomena, as I just now I introduced to you, is includes mass transfer. Okay, so mass transfer we will do with diffusion of flux. Okay, with Fick law. Okay, so you have first um, the first Fick law and the second law. Okay, so and you will study the mass transfer in gases, liquids, and solids. Okay, for liquids, maybe you it includes a molten metal. Okay, it means the metal or alloys. Okay, alloys, melt alloy, melting alloy, and solids. Of course, you mainly you study in metal. Okay, and can be a polymer or ceramic. Okay, but maybe in this course, Dr. Hai, or in this course, maybe we will focus on metal. Okay, and for the energy transfer, it includes conduction. Okay, we have three different transfer modes: conduction, convection, and radiation. Okay, so for momentum, so it will be momentum flux, viscosity of glass liquids. Okay, so yeah, of course, for conduction, you already know Earth, surrounding us. Okay, for example, this picture illustration of three different modes of conduction. Okay, radiation, conduction. Okay, and convection. You can see this. Okay. So, can you take note?
Yes.
Okay, thank you. Okay, so we start with heat transfer. So, So why we have to study heat transfer and what is heat transfer? So what is the role of heat transfer in engineering? Okay, heat transfer is a fundamental part of thermal engineering. Okay, this is a fundamental part. Course is very important. Okay, so for thermal engineering, so it's appear everywhere in our life. Okay, and surrounding the environment. So you can see uh, thermal engineering from heat exchanger. Okay, you can see from air conditioning. Okay, you can see yeah, from is also involved to not only heat exchanger is also involved to for example in metallurgical. Okay, is involved to our field. Okay, in metallurgy, for example uh, cutting. Okay, for some casting and steel production. So this is involved to heat transfer engineering, and it also involved to electrical engineering, nuclear, of course, nuclear. Uh, you know that nuclear power plant. Okay, yeah, I'm sorry. Uh, so it is this heat transfer is a sign of the rule governing the heat, the transfer of heat between the systems of different temperature. So I have to remember that heat transfer is between the system of different temperature. Okay, different temperature. So this is a very important thing, and this is a fundamental thing. Okay, for heat transfer. So it will appear between the system have different temperature. Okay. So in the thermodynamic, okay, the heat transfer from one system to its surrounding is assumed, okay, as a given process parameter. Okay. So the question is this assumption does not give any information on how the heat is transferred. Okay. Is this assumption does not give any information on how heat is transferred? Okay, and quick rules determine the quantity and rate of the transfer heat. Okay, so quick rules determine the quantity and rate of the heat transfer. So this all the question we will answer in the following part. Okay, following section. Okay, and of course the following slide. We will approach. Okay, approach one by one, and we will approach from a simple concept to a complicated, complex equation and complex problem. Okay, so question are what is a heat transfer? Of course, I already told you something about heat transfer, but for the course, okay, so we'll have to answer what is a heat transfer. Okay, heat transfer. So heat transfer is exactly what is a heat transfer. So heat transfer is the transport of thermal energy. Okay, is the transport of thermal energy. Okay, due to a temperature difference. Okay, as I just mentioned you, the uh, the heat transfer is happen because the temperature difference or temperature gradient. Okay, the difference here from a cold side to the hot side. For example, you have a one bar, a steel bar. Okay, one side you, the temperature high temperature. Okay, other side is have a lower temperature. So the heat transfer will take place. Okay, so that's why it's mentioned that the heat transfer happen when or due to a temperature difference. Okay. Okay. The second question is where is heat transfer applied? Okay. So all these questions answer or ask by asking and answer this question. So will help you more uh, clearly understand or image about this course and image about uh, yeah, of course, the content of this course and help you have can properly design process. This will help you properly design process by asking this question. So the second question is okay, where is heat transfer apply? So if a temperature difference is present within a system or between system, okay, in thermal contact to each other, heat transfer will occur. Okay. Okay, so within a system, it means that, for example, solid, uh, one solid object. So that's we consider one system, one homogeneous system. Or between systems, it means you have two. For example, you have two different steel bar, but it's in contact. Okay, and both of them have a different temperature. So the heat transfer will also take place. That means uh, between system. Okay. Do you understand this? Uh, so please okay, interact. Okay, because if you keep silent, okay, I don't know you understand or not. So please respond. Okay, respond to my question to make sure that you understand or you not understand, so we can discuss. So one person, let me know. Do you understand the second question?
Yes. Yes.
Okay, so make sure that you understand from very simple thing and very simple concept. Okay, so later we move is more complicated thing. Okay. Okay. So we will move to the next slide. Okay, here we have three different modes of heat transfer, as I mentioned you earlier. Okay, so we have conduction, thermal conduction. Okay, so we have a different temperature from one side to the other side. For example, you have one bar here. You have this side. You have a temperature T1, and this side you have a temperature T2, and T1 higher than T2. Okay, so the heat transfer will take place from T1 side to T2 side. Okay, this is a vector indicate the direction of heat transfer. Okay, so this is the thermal conduction mode. Okay, the second one will convection. Okay, convection. Convection, yeah, from surface to moving floats. This happen due to the moving of floats. Okay. Uh, can one person give me an example about his convection? Anyone? Heat transfer by convection. Anyone can give me an example? Yes.
Like when you boil a pot of water.
Yes. Yeah. Right. So, what is the behavior when you boil a pot of water?
The water inside moves up and down.
Okay. So, yeah. So, what water will moving up? Which one will moving down?
The hot floats on the top surface, and the cooler one drops into the
Go down to the bottom, right?
yes.
So, do you know? Why this happen? What is the reason? Do you know?
Because the hot water is like way is lighter than the cold water, so it floats on the surface.
Right. Yes. Because on the surface, the water is cooler, right? So
It's
have
lighter.
it have a high density. We call it a high density. Yes.
Yes.
Yeah. So the at the bottom it have a hotter and a lower density. So it's wheel moving up. Oh, first, yeah. Thank you. Is it me?
My name is Hương.
Hương. Okay. Thank you, Hương. Okay. So we also have yes, Grace. We also have other example for moving for convection, for thermal convection. For example, you fire the wood, right? Yeah, you go somewhere. For example, you go for picnics when you fire the wood, so you can feel the air is moving up, right? So that's also happen for his convection phenomena. Yes, so that's another example. Okay, the third one we have thermal radiation. Okay, this is the third one, thermal radiation. Okay, this thermal radiation conduction. Okay, so this is different from the first two modes. Okay, so we will study more detail, but this you also can experience every day, or you also already know about this. But another person can give me where is the thermal radiation happen, or where you can see this heat transfer most. Okay, okay. Anyone? Anyone can give me example about what you know about thermal radiation and example about this? Don't know?
Is that
What's your name?
my name is Dung.
Okay, Zoom. So, can you give me an example?
When the sun is rising, so when we go out and inside the sunlight of the sun, so
Okay.
so my skin become black, more black,
Black,
and
okay.
yes, and I feel hotter in skin. I think it's a thermal radiation.
Okay, so those skin is up like something like burning, right?
Yes.
Okay, thank you, Zoom. Okay, this is exactly our Earth receive the heat, okay, from the sun also by thermal radiation, okay, transfer, okay. That is you can experience every day, almost every day. Of course, in the winter time you cannot experience this, but obviously in the summer, okay, you can feel this very clearly, okay. So that's a general thing. You can see we have three different modes of heat transfer. One is thermal conduction, second is convection, and thermal radiation. So we have some very simple idea about the heat conduction, okay. Okay, so we go a little bit more detail about what is a heat conduction. Okay, so we our approach is step by step. Okay, if first we go very general and very simple. Okay, so we make it more clear. Okay, clearer. Okay, so for the first conduction, okay, it is his conduction. Okay, but heat transfer is his conduction. So in heat transfer or conduction, okay, or we call it heat conduction, is the heat transfer of energy. So remember this transfer of heat energy. So you have many different energy. So in this case, is about the transfer of heat energy. Okay, heat energy. Okay, by diffusion. Okay, you remember this by diffusion and collision of particles. Okay. Okay. The heat transfer. Okay, is the transfer of heat energy by diffusion and collision of particles or quasi-particle, okay, within a body, okay, within a body due to a temperature difference, due to a temperature difference, due to temperature difference, okay. Okay, this okay, as I mentioned earlier, is not only apply for a system or a body, but it also can for the system is have a different body in contact. Okay, in contact also can apply, but in this definition, okay, that give you one very simple and you can imagine how the heat transfer will happen. Okay, so please remember, okay, heat transfer is about the transfer of heat energy, okay, by diffusion and collision of particle or quasi-particle, okay, in a body, okay, due to temperature difference. Okay, so this is about heat conduction. Okay, so we will discuss what is a diffusion and collision of particle. Okay, so that is driving force, or that is for heat conduction. Okay, yeah. So in this case, this is a microscopic level mechanism. Okay, so we have so as above. Okay, this above definition is for a microscopic level mechanism. Okay, microscopic. Okay, and you have a microscopic and macroscopic. For microscopic level, it means that we consider the object in the scale of atom, molecules, and other particles such as electrons, okay, electron and proton. Yeah. So that is what we call is a microscopic level mechanism. Okay. So we have, of course, we also have a microscopic level. And someone give me example of macroscopic level. Do you know, for example, macroscopic? This is micro, right? Micro. We have macro. Do you anyone know about macro? Okay, we have a microstructure, right? You study, and yeah, you micro structure. So yeah, of course. So we also have macro. So do you anyone know about macro? Chami, do you know macro? Any example? What is a macroscopic? Scopy?
Macroscopy, that means the thing that we can use a naked eye to see.
Yeah, right. For example, can you give example?
When we hit a bowl in the oven, and then the bowl is rising the heat also as well.
Okay. Okay, thank you, Chami. Okay, so it's a very simple. For example, the hair. Okay, you can see by the neck to eye, by the eye. Okay, so that is one example of macro. For example, yeah. Or the macro is mean with a scale of a micrometer or millimeter or meter object. Okay, so you can see by the eye, or you can see by some optical optical microscope. Yeah, so that is okay. So go back to our lecture. Higher temperatures are associated with a higher molecular energy. Okay, so we will explain why heat will transfer from hot side to from hot side to cold side. Okay, so this we will explain. Okay, so high temperature are associated with a high molecular energy. Okay, and heat energy will be transferred from the more energetic to the less energetic molecular. Okay, so this is a mechanism of heat transfer. So if we anyone or I ask you the question, what is the mechanism of heat transfer? So you are able to answer, okay, based on this mechanism. Okay, so it's because, okay, of heat transfer from higher molecular energy. Okay, okay, so heat will transfer from okay, hot side to cold side, because from hot side if receive higher energy, so the particle, for example, atom or electron, is become excited. Okay, excited, and it will transfer energy to the neighbor. Okay, the neighbor particle, which have less energy. Okay, so that is the mechanism of heat transfer. Okay. Internal energy diffuse as rapidly moving or vibrating atoms and molecules interact with labeling a particle. Okay, so this is also involved to the mechanism of heat transfer. Explain to you how heat transfer from hot side to cold side. Okay. Okay. So yeah. So the particle rapid moving or the atom vibrating when it receives energy. Okay. Okay. So it's will interact with neighbor which have less energy, and the neighbor one after receive energy is become more excited. Excited. It means it will have more energy and it become excited and vibrates with more high frequency, and it will impact, okay, or college to the neighbor one. So the energy will be transferred, okay, from a hot side to cold side. Okay, so this is a mechanism of heat transfer. Okay, so please take note. Okay, so for the as an engineer, so you have to understand the fundamental thing. Okay, so not just about you see at a macroscopic, okay, level, but you have to also understand, okay, and know about this phenomena under microscopic level mechanism. Okay, so this is important, very important, okay, for or as engineer. Okay. So here one illustration or a schematic representation of generation lattice moving, okay, of atom, okay, of atom, okay, of atom when it receive energy, okay, or of course in a normal condition it also vibrates, but when it's receive energy it's become more exciting, right? So this is give you image how the atom, okay, it transfer energy at the normal condition. Okay, this is normal lattice production for atoms. You see So the atom can moving around its pendulum, okay, its pendulum position around, okay. But when it receive more energy, it's become more exciting, okay, more exciting. So it will vibrate with high frequency, okay. So it will transfer from one to the neighbor one, okay. So the neighbor which keep receive a higher energy is will also become more excited and will transfer energy to the next neighbor. So as this flow, so the heat will transfer from hot side or from the side which the object receives the energy to the side is have a colder, okay, it means less energy, okay. So here is at a microscopic level, okay. So, okay, so the next we want to know where is conduction is dominates, okay. Is it in solid or in liquid or in gas medium, okay. So the answer is conduction, okay, or heat conduction is the most dominant heat transfer within a solid, okay, within a solid or between solid object in thermal contact, okay. So you remember the conduction is dominant, okay, in solids, okay. Okay, so why is dominant in a solid? Okay, the question why in solid, why heat conduction is higher in solid but is less in liquid or gas? Okay, so we have to also want to know about this. So conduction is greater in solids for some reasons. Okay, conduction is greater in solids for some reason. Because the network of relative close fixed spray of atom. Okay, because the space or distance between atom in solid is will much shorter compared to the distance between atom in air or in liquid. So that is the reason. And yeah, of course, so if it's more closer to each other, so of course it's easy to transfer from one to another one, right? So that's why, okay, that's why the heat is dominant, heat transfer dominant in solid. Okay, so it's that is one reason. This is only one reason. We have more reason. Okay, why is in okay. So for yeah for the gas or the liquids, okay, it's less conductive due to large distance, as I mentioned, okay, between the atom. So it's fewer collision or fewer or less contact or collision between atom, okay. So less conduction. Okay, this is the first reason why, okay, why the heat conduction in solids is much higher compared to the liquid or gas. one thing also remember that the conduction increase with increasing temperature. For this is for liquids and for gas, for gases, okay, for gas. So the conduction increase with increasing temperature, and also increase with pressure, also pressure. Okay, that it in fluid. Fluid it includes liquid and gas. Okay, so conduction will increase with temperature and with pressure. So anyone can explain to me why? Okay, why the heat conduction in gas or in fluids, okay, increase with temperature and increase with pressure? Anyone? Anyone can explain about this? Or silent?
When we increase the temperature, the atoms move faster, so it easily transfer energy.
Okay, right. Yeah.
And
how about pressure?
And when there is pressure, I think the atoms are closer together. The distance between atoms is shortened.
Okay. Yes, yes, that's right. Yeah, you yes. When we increase temperature, so is the atom become more excited, so it's moving or move around, so it will have a higher chance, okay, to interact to each other. So the energy will easy to transfer from one to another one. And yeah, of course, she also explained it's right. When we increase the pressure, so the distance between atoms will more closer. Okay, so the heat easier for heat transfer because the atom when atom closer, so it have more chance to interact. Okay, so the energy will easy to transfer from one to another one. Okay, that is the reason. Okay, so this is about the distance between the atom. We also have other reason why. Okay, and we also want to know about for the solid. We also have many different kind of solid. For example, we have metal, we have a polymer, we have a ceramic. So we also interested to know. Interesting. It's also interesting to know that about the heat transfer in different kind of material. Okay. So I think you already know that the heat conduction in metal, okay, will be the most higher compared to ceramic or especially for polymer, right? So what's the reason? Okay, so we will go to know. So for the metal, okay, for example, copper and aluminum, silver are usually good conductor of thermal energy. Okay, what's the reason? Because metallic bonds, okay, metallic bond have a free moving electron, so the heat, so the transfer thermal energy rapidly through the metal. Okay. It means that the electron also is one mean to transfer or transport the energy in metal. Okay, so electron also play a role in transport heat energy. Okay. Okay, as you know, that the metallic bond is a weak bond. So because the electron in the metallic is can moving free moving around the atom, right? Yeah. So that's why it's also easy to carry out heat. Okay, moving. Not so in the atom, heat transfer not only by vibration atom, but also by carry out by free electron. So that's why in metal it have the highest or very high thermal conductivity compared to ceramic or polymer. Okay. So take note that electron conduct both electrical and thermal conductivity. Okay. So electron conduct both electrical and thermal conductivity. Thermal conductivity. Okay. Okay. So how about for example polymer or ceramic? You know ceramic have less thermal conductivity compared to metal. Anyone know why? For example, ceramic, yeah, ceramic, alumina has less conduction compared to copper. Why? Anyone know? Also, it's a solid object, right? But heat transfer in copper is much higher compared to a ceramic. Why? Do you know? Anyone know why? So of course it involves to the bonding, okay? Because at I said metallic have free electron moving, right? But for ceramic, it have covalent bonding, okay? They don't have free electron. They don't have free electron moving. So that's why the heat transfer is less than in ceramic compared to metal. Okay, so please you can read more from literature for this, and also of course for a polymer also. Okay, so we go to introduction for the second mode of heat transfer is convection. Okay, the heat conversion, okay, or heat transfer by convection is from one place to another place by the moving of fluids. Okay, by the moving of fluids. Okay, by the moving of fluids. The convection is usually the dominant form of heat transfer in liquids and gases. Okay, so it's dominant form of heat transfer in liquids and gases. The convection can be forced. Okay, this is very important for thermal engineering. Okay, it can be forced. Okay, we have a natural convection and we have a forced convection, so it's very different. But for the forced convection, it's very important. Okay, the convection can be forced by moving of a liquid by external means. Okay, by external means other than buoyancy force. Okay, for example, a water pump in an automobile engine. So we call it forced conversion. Okay. Or for example, if you stay in one environment, okay, you stay in the house, for example, if you feel cold, but actually you stay in the house, the body, okay, exchange the heat with the environment. So you, of course, environment can be have a lower temperature than the body. So heat from the body can transfer to surrounding environment, right? But you still feel hot. But if you use some external mean, for example, fan, so you the body you feel that is more cooler, right? So that is a, we call it the forced convection. Okay, so it will make the heat, okay, heat transfer more faster, so the body can feel more cooler. Okay, so for the forced convection, okay. Yeah, here, yeah, explain, for example, in a natural convection, when you boil water, or in you burning wooden, or you use, yeah, indoor house, okay. This is a flow of uh, air, okay, in the house, yeah, with current. Heated air will, yeah, air rise to the top, okay, because it have, as you mentioned before, it have a lower density, okay, and the heavier air, okay, from the top will moving down, replace the cooler air, okay. So please, this one can, the forced convection also can apply when it happen when you apply, for example, air condition, okay, air condition, okay. So please draw some simple, okay, some simple schematic for illustration, okay. And when you take the exam, okay, so you also need to draw some simple schematic for illustration, what you explain, okay. Okay, maybe we take rest for 50 minutes, and we come back to study. Is this okay?
Yes.
Okay, so we will come back to 8:20. Okay, 8:20.
Okay.
So after we come back, maybe we have to move faster, because the content of pitch transfer is very large. So maybe we have to moving faster. Okay, so we take the rest for 50 minutes. Okay, we continue the class.
Okay.
Also, okay.
I'm here.
Lộc Thị Yên, is this already in class? Lữ Duy Nam.
Có.
Nguyễn Đức Mạnh. Nguyễn Đức Mạnh.
Có.
Nguyễn Đức Dương, Nguyễn Quốc Dương.
Có.
Nguyễn Thùy Hương.
Yes.
Okay. Nguyễn Văn Bình.
Yes.
Okay, so we we continue the class. So now we have to moving faster. Okay. Okay, so we have a forced convection. Okay, of course, we also have a natural convection. So in some cases, natural buoyancy. Okay, force, natural buoyancy, force. Okay, so you know the buoyancy, right? Buoyancy force alone are entirely respond for a fluid motion. Okay, when the fluid is heated. So this process we call it a natural process. It means the process is the particle always moving by buoyancy force. Okay, not by external mean. Okay, so this we call it a natural convection. Okay, natural convection. Okay. Okay, for example, okay, the air moving, okay, from hot region to the cold region, okay, or the opposite direction, okay. For example, the sea breeze, okay, the cool sea breeze air, okay, moving to the continent, okay, and the warm air will or hot air will move from the land to the sea. Okay, this is a natural convection. We call it a natural convection. Okay, we go to the third radiation. The third heat transfer mode is a thermal radiation. So the thermal radiation is energy emitted by matter as electromagnetic wave. Okay. Okay, this is by electromagnetic wave. And the important thing here also need to take note is that heat transfer by radiation does not require the presence of matter. It means that it can transfer in the vacuum, okay, vacuum. But for heat conduction, you have to have the matter, okay. Heat conduction, okay, or convection cannot transfer with matter, okay. But for heat transfer by radiation, it does not require the presence of matter. Okay, that is a different from thermal radiation and heat conduction by conduction and convection. Okay, electromagnetic wave also transfer energy in empty space. As I said, it can transfer in a vacuum. So the heat received on Earth from the sun is by the traveling from Earth electromagnetic wave. Okay, you can see, yeah, the heat we receive on our Earth from the sun is transferred by radiation. Okay, radiation. So for the information, any object with have temperature greater than 0 degrees, it will emit the radiation. Okay, not only the hot we feel like hot water or hot bar is 100 or few hundred degrees C, but any object which have a temperature is mean higher than 0 degrees C, so it can emit the radiation. Okay. So we will go to some another definition. Okay, one is about heat rate and heat flux. Okay. So heat rate we call it rate of heat transfer. So we note it at Q. Okay. So the rate of heat transfer is the amount of heat transfer per unit time in material. Okay. So each unit will be watts or joule per second. Okay, joule per second. Another important parameter is the heat flux density. Okay, heat flux density we denote as small q. Okay, is equal to big Q divided to A. Okay, A is mean area. Okay, area. So this heat flux density defined as the rate heat transfer per unit area. Okay, so it will have unit is watts per square meter. Okay, watt per square meter. Okay, this both heat rate of heat transfer and heat flux have direction. Okay, and magnitude. So here is example. Here is direction of heat transfer per area. So this we will call is the heat flux density. Okay, heat flux density, heat flux. Okay, through a surface area. Okay, so density is mean something divided to can be the volume or surface area. But in this case, for heat transfer, we will consider how much of heat is transferred per unit area. Okay. So heat flux, or sometimes we call it heat flux density. Okay. So density, as you know, the density, right? Okay, we go to the next definition is about thermal conductivity. Of course, this you already heard about it. So thermal conductivity, this is denoted as kappa, not K. Kappa, okay, is a material property, okay, which is defined as the quantity of heat Q transfer in a time T, okay, through a thickness L or delta. So sometimes people use L or sometimes use delta, okay, in a direction normal to a surface area A, okay, due to a temperature difference delta T, okay. So we have partial derivation, okay, derivative, okay, Q respect to T, okay, equal to minus AK delta T, okay, divided to delta. So this is this equation, okay. So y rate of heat transfer equal to so this we can explain rate of heat transfer per unit area, okay. This will rate of heat transfer. This equation mean rate of heat transfer, okay, will proportional to area. It means that we have big area, right? So the amount of heat transfer will higher. And of course, the temperature difference between two different positions. So the rate of heat transfer also will higher. So rate of heat transfer will proportion to temperature difference, delta T. And of course, if the object is thick, so the rate of heat transfer will smaller or reduce. So that's why we divide to thickness or delta here. But for different materials, they will have different behavior or ability to transfer of heat. So we put here one constant or one coefficient, what we call is kappa. Okay, so here kappa here is represent for the ability to transfer of heat for different material. So we call it thermal conductivity, kappa. Okay. So kappa will Q we have unity watts. So kappa we have watts per meter Kelvin. Okay, watt per meter Kelvin. So kappa is we call is thermal conductivity. Okay. To quantify the ease with a particular medium, okay, conducts energy employs in thermal conductivity and also known as thermal conductivity constant, okay, constant. So kappa here is constant, okay, or we call it conduction coefficient. So we denote the as kappa or lambda, okay. So this is about thermal conductivity. Okay, thermal conductivity. So here is some thermal conductivity of some material versus temperature. So we can see here that water, air, and other gas, so have very low thermal conductivity. Is less than 1 watt per meter Kelvin. You can see here in this area. But for the solid one, for example, even water, it can, when it become ice, so the thermal conductivity also increase, okay, around 4 to 2 watt per meter Kelvin. You can see here. Okay, so for ice, you see that when the temperature increase, it means ice is slowly become liquid, so the temperature, the thermal conductivity will reduce. Okay, you can see here. And for other solid, for example, metal or alloy, for example, outstanding steel or ferric steel, okay, the thermal conductivity now become very high already, about 60 watt per meter Kelvin. Okay, and of course for other metal, pure metal, for example, aluminum, gold, copper, or silver, the thermal conductivity is much greater, and you can see that the silver have thermal conductivity above 400 watt per meter Kelvin. So for the copper, the thermal conductivity around 400 watt per meter Kelvin. Okay, followed by gold and aluminum. Okay, so you can see. Yeah. So we will go some specific problem with the design process. Okay, which involve to heat and mass transfer. Okay, the first one we consider for the design. Okay, and application involved to the heat transfer. For example, in we need to control or manage the temperature in the room, okay, in the room. You can see this room have temperature, for example, TR, and we have one heat exchanger or radiator here, okay, radiator. Okay, this kind of radiator, especially in European, especially for some country very cold, for example, Nordic country, Sweden, okay, Norway or Denmark or Sweden, okay. Usually in the winter time they use radiator, okay, to heat or make the house warm, okay. Yeah, this kind of radiator to warm the house I has already experienced in Sweden, okay, in the winter time. So this kind of radiator, you have one inlet, hot water, okay, flow in, and other cooler water will have go out to the outlets, okay. So the hot water flow in this radiator will make the room warmer, okay. So the thing here is, the question here is, what suits the surface of the radiator, okay? It should small or big, okay? So there are some problem or some matter the engineer need to consider, okay? For small surface, so it means that if the temperature from a radiator, okay, transfer to the surrounding environment in the house will be small, okay, and of course it take a long time to warm up the room, okay, that is a problem. But another side, if you use a small surface, okay, it means the area of contact area between the radiator and the room is small. So of course the cost for production of this radiator will less, okay. You have some disadvantage and advantage, okay. So if we want to have a big surface, okay, so we more temperature and faster the exchange heat between the surface of a radiator and surrounding environment, okay. Of course this house can be warm up faster with big surface of a radiator, and if you have you also will have another side with different this big surface, okay. So you will have pay more, okay, or the cost of this big surface will be higher. So for the engineer, you need to optimize, okay, between small surface and big surface. You need to optimize between the cost and the rate of heat transfer. So that's why you have to study this course before you are able to design, okay, any process, any equipment, okay. Yes, this is one of the problem you need to consider, okay. So in practical design of apparatus or yes, or complete plans, okay. Such if in the plant, very large, okay, automobile, or you see in industrial plant, right? The heat transfer, okay. Besides the technical science, thermodynamics, fluid mechanics, material side, you have to choose what is a suitable material for this plant for the construction, right? And mechanical design. So you have to consider the science of heat transfer, okay, or what we call is the science of heat transfer is required. So the goal is always to optimize and improve the products. The main goals are to increase efficiency. Okay, efficiency is mean we want much heat transfer to surrounding environment in case of radiator in the winter time, okay, or if in case we want to cooling down some object, we want the efficiency cooling is higher, okay. Okay, so we also have to optimize the use of the resource, okay. The resource is limits, right? So we have to optimize, or we have to use with the high efficiency. So that's why engineer have to study, okay, to find which the optimal way, okay, to use the resource with cheaper and high efficiency. Okay, so need to reach or minimize environmental burden. So as you know now, that's we have environmental problem, right? Yes. So a lot of gases after burning is emits gases CO2, right? Carbon dioxide, right? Carbon dioxide. Yeah. So it's have problem with polluted, okay, and the health impact to the health of the human. Okay, so you have to optimize, okay, minimum the environmental burden. Okay, it means that you have to improve the efficiency, okay, efficiency of consuming energy. And the last one, we have to optimize product cost. So we have to design the process to reduce the cost. Okay, so everyone can approach the products. Everyone can can buy or can use the products. So heat transfer will involve a large aspect of thermal engineering. It includes heating, ventilating, air conditioning system. Okay, it involves to thermal power plants. Okay, this is very important. Thermal power plant to produce electricity. Okay, refrigerator and heat pump. Okay, gas separation and equals fraction. Okay, cooling of machine. Okay, processes are requiring cooling and heating. Okay, heating in metallurgy. Okay, metallurgy. For example, in um, steel production. Okay, in casting process, heating up or cooling down production parts. For example, annealing. Okay, annealing or heat treatment some parts. Okay, for example, we need to before we can use gear, okay, or any parts, we need to heat treatment to make our parts become stronger. Okay, so that we need to it involves to heat transfer. Okay, also involved to solar thermic system. Okay, nowadays you can see a lot of solar cell. Okay, use a lot of solar cell. Okay, so solar cell is can combine with heating water heating system. So you can use the water hot water free. Okay, instead you have to use hot tank in the house with electricity, so you have to pay to the government, okay, to heat the water. But by integrated solar and thermic system, so you can produce electricity. Besides, you also can heat up the water, okay, so you can use hot water free. Okay, also involved to combustion plant, okay. So all this involve a lot of area is involved to heat and heat transfer. Okay. So here and a little bit more detail about heating radiator. Okay. Yes. In the it can be in the center heating system, hot water or sometimes steam. Okay, is generated in the center boiler. Okay, and circulates by pump through radiator. Yeah, radiator. Okay, here is a last radiator in a house. You can see. Okay, especially in cold country. Okay, they use this. Okay. So of course, the earth frontage using this kind of radiator is very safe. Okay, only hot water and no gas emission. If you burn wood for heating, of course, it can emit CO2 and so other toxic gases, right? So it's very safe for use this kind of radiator. Okay. As I mentioned, so problem is are how does the radiator warm up the room? Okay, the behavior. So you have to study, so you know that's the behavior to heating up the room. So you can control it. Okay, so you can design or you can optimum. Okay, optimize. So what is the surface area of radiator? The radiator should be used. Okay, as I this question, okay, had discussed before. And what are the water temperature in and out? Okay, so all this you have to consider. Okay, for design process. And also very interesting example. Example here. You have a very nicely window here. Okay, in the winter. Sorry, in the summer you want to have a very large window so you can see very nice landscape outside, right? So but in the summertime the heat from the sun, okay, will warm up the house, okay, and you need to the system need to consume more energy to cool down, okay, to cool down the house. Okay, if you have more large window, so you have to spend more energy to cooling or keep the house cooling. Okay, of course you have nice view, but you have to pay more uh, cost, okay, or energy. In the winter time, okay, the heat loss from the house to outside. So this problem you also need to study. Yeah, how is exchange the heat from inside to the outside or in opposite side from outside to inside. So this will involve to heat transfer. Okay, so it will involve to the size of the window and the thickness of the glass you use for window, and it's also involved to what kind of material or what kind of glass you use. Okay, some glass can be have very high, can have a high thermal conductivity. Some glass is have less or lower thermal conductivity, so it can um, uh, insulate or isolate the house to the outside environment. Okay, or so you can design some kind of glass. It have vacuum in the between layer, so it also prevent the heat transfer. So yeah, I mean, yeah. So that is this is many problem or many issue we need to um, uh, know. Okay. So yeah, so the third question is the size, thickness, thermal conductivity of window glass. Okay, in order to save energy. Okay, you have to optimize between the fueling have to have very high, a very large window, and one side we have to pay for energy consumption. Okay, or you have to use some high techniques to produce with very large class, but it can isolate. Okay, isolate with outside environment. Okay, this similar for heat transfer from radiator, so you can I will skip this part. Yes, this radiator using for car, okay, to cooling the engine, okay. So some question is have to involve here, okay. What are the heat transfer process to air, to radiator, and inside the radiator? So this involve all three modes of heat conduction, okay, in conduction, okay, and convection, and even radiator, okay, radiation, radiation. Okay, so the question also involved to what side of radiator and cooling fan velocity. So this is involved to forced convection. So what are the suitable material for this application, and so on. Okay, so we have to know. And here for power plant, okay, for power plant, also very important. Okay, it involves to the thermal, the heat transfer. So you know that's to rotate the turbine. So water needs to need to heat up into the steam, right, with high temperature and high pressure to rotate the turbine to generate electricity. Okay, so problem is how this steam, how this water steam transfer from the boiler center to the turbine radiator generation. Okay, so on the way of transport heat steam from the boiler center to the turbine generator, it can be lot. The heat can be lot. Okay, so how we design, okay, our pie, okay, what kind of material or what kind of pie we should use to reduce the heat loss. Okay, so here is involved to the material of the pie and how we use the insulator to prevent the heat loss. But it's not only simple to use a insulator to apply the insulator to reduce the heat loss. It also involves to optimize the cost. Okay, if you use a very thick insulator, of course you can reduce the heat loss, but you also have to pay more cost for this. Okay, and other thing you also need to know. Of course, you after study this course you will know. Okay, it's not only you increase for infinity thickness. I mean it have a certain thickness of the insulator is sufficient for or sufficient to prevent the heat loss. Okay, even you increase more, the efficiency of prevent heat loss also not increase. It's just only waste of material and less to waste of money. Okay, that is another problem. Okay, so as I can illustrate here, one is heat loss at rest. Okay, and this axis is about the thickness of insulation. So you can see the heat loss will reduce as we increase the thickness of insulation. Okay, insulation. But after a certain of thickness, okay, so the heat loss will be constant or minimized. Okay, so we as engineer you have to find this master or this kind of value. Okay, this value. Okay. We also this heat transfer also involved to in electric chamber or furnace, especially for heat treatment. For example, we have a brake or some part of machine, for example, bearing, okay. Any parts we need to heat treatment. So how we need to design this uh, furnace, okay. In the industry we call it a continuous furnace, okay. We want to this is besides this room temperature. So when we want to after finish one circle, okay, it means when we put the sub parts or object here after it go out to the furnace, so we can finish finish the heat treatment, okay. So the question here is, or the problem here is, if the velocity of the roller is constant, okay, this roller to move, for example, to move the object, okay. So what is the length of the chamber that's to design temperature and time, okay. So yeah, the line of this, okay, furnace have to decide to match to after finish the circle of fitting, so they can finish the heat treatment. So the line here is involved to the velocity of movement and the temperature, okay, and the time. So we have to we have to optimize all these parameter, okay. Right. So in case if line is constant, okay, so what is the velocity of roller should be applied, or what is the temperature, okay, and so on. We have to consider. Another a problem we need to design for the main board in the computer, okay, is involved is including a lot of parts in the board. For example, microchip, okay, chip or transistor. Here is transistor. So during working, okay, the transistor is increased temperature. So it, you know, that's when the transistor increase at a certain temperature, the computer will shut down for safe, okay. So and the tracing temperature during working of transistor also involved to the lifetime of this transistor, okay. So people apply air to cooling down this transistor. So the life of transistor, you can see roughly, you can see in this picture, okay. If we transistor temperature can cooling down, okay, so the life of transistor can prolong, okay, okay. So we have to make so the problem is here is what is the velocity of airflow to maintain a transistor at desired temperature, okay, velocity. So the fan here, we need to apply the fan, okay, to make forced convection. If by natural convection is not enough to cooling down a transistor, okay. So some transistor will stop working after temperature rise about 50 or 60 degrees. So you have to use forced convection, okay. So this in electronic devices also involved to heat transfer. And for the mass transfer, in case the mass transfer is involved to diffusion of atom, okay. Here one very famous example is for carburization, to make the surface of the parts, okay, the object become harder and the wear resistance increase, okay. For example, this is bearing. So we normally apply carburization, okay, to make this hard, okay. So carburization is involved to the diffusion a carbon atom into the hot iron atom in the surface of object. Okay, object. So it make this harder. So it also involved to mass and heat transfer. Okay, and heat transfer. Okay, so for fluid or momentum, Dr. Hai will give you a introduction and application. So for my topic, so is for introduction is will be stop here. Okay. So anyone have any question about this before we can move to the next topic? Any question? No question. So no question is mean you understand.
Yes.
Okay. So I feel that is we still need to move faster. So you record so you can go back at home and study. Okay. So. Can you see my slide? Anyone?
I haven't seen it. I can't see anything.
Okay, so okay. Can you see?
Yes.
Yes.
Okay, so the next lecture will be, we will study some fundamental laws of heat transfer. Okay, and okay. So the law of heat transfer, we will study fundamental laws. It including a law of conservation mass. Okay, law of conservation mass, Newton laws of motion. Okay, and also the law of thermodynamics, the first and the second law. So of course, the law of thermodynamics you will already study. So I just give you briefing on this topic. Okay, and we have some subsidiary laws. Fourier's law of heat conduction also very important, and Newton laws of cooling, and the law of thermal radiation is especially Stefan and Boltzmann law of radiation. So in this lecture will involve to we will study the law of heat transfer. Okay. We have the continuum concept. Okay. So here for the matter is we have to define some. We have some concept. We have some concept. Okay. First is matter is composed of molecules, atom, and electron. Okay, in constant motion and undergoing a collision. Okay, this is some concept we or some definition. Okay, concept we have to introduce to you before we need to go in detail. Okay, so this Okay, this is the most fundamental approach in analyzing the transfer of heat in substance by conduction, and is to apply the law of motion and each individual particle or statistical group of particle. Okay, so yeah. So this is the matter. Okay. And the more problem with engineering is primary interest in not in molecule behavior of substance, but rather we interested to know how the substance behavior as a continuum medium continuum. For example, you just see the bar, one steel bar, okay, that is consider one continuous medium, okay, it's homogeneous. Yeah, sometimes we so in as engineer you not consider as a molecule or atom level, okay, so we just consider our object as continuous medium, okay. So this one for the information. So let's we when we talk about the object, it means continuous medium. We don't consider a small small level, small scale. Okay. So thus in his conduction study, we will ignore the molecular structure of the substance and consider it to be continuous media. Okay, that is the thing we have to tell each other before we start to study. Okay, and we go to how we will study heat transfer. Okay, so I will give you how we approach the problem and how we solve problem. Okay, so I will introduce you a step to approach the problem. Okay, so beside profound knowledge of basic law, and the engineer has to know the methodology, how to apply the above mentioned basic law and principle to concrete a problem. Okay, so it's important to learn a systematic analysis of problem. Okay, this is very important thing to approach or to solve problem. And this consists mainly of 6 steps. Okay, so I will explain to you, or we will discuss the 6 steps, how do we analyze it and how we approach the problem. Okay, so the first step, okay, the first question, okay, is what is given. Okay, for any thing you study, first thing you have to know what is the problem. Okay, you have to identify the problem. Okay, so analyze what is known about the problem. You have to investigate, or other words, you have to know about the problem. Like you go to, you want the doctor want to treat your health, so he have to know what is the problem. Okay, before he can treat the health. Okay, so note all the parameters which are given or may be necessary for the further consideration. Okay, the first thing you have to know the problem. What is the problem? So the second step, or the second question, what are you looking for? Okay, what are you looking for? Okay, you already know the problem. So what are you looking for? What do you want? Okay, so at the same time as the first step, analyze which parameter has to be determined. Okay, and which question have to be answered. Okay, so this is the approach. Okay, but I think is, oh, okay. The finish, right, the class, the time out, right? Okay, so we need to stop here, so we will continue in next week. Okay. Okay.
Yes.
Yes. Yes.
Okay, so we have to stop here.
Bye, teacher.
Okay.
Bye.
Okay, bye bye.
Thưa thầy gửi lại cái slide lên nhóm được không ạ?
As I mentioned earlier, I will not give a slide lecture notes, so you have to take notes, or you can record and you can study at home. Okay. So I think someone already record here, so you can download the video or the lecture. Okay.
Yes, teacher.
Okay. Thank you. Okay, so someone stop the record.